Good morning, everyone. Welcome to Introduction to Electronics and Communication subject. Myself, Darshan B, Assistant Professor, Department of ECE, SJBIT. So today we are going to discuss some topics from Module 1 on Introduction to Electronics and Communication. Rectifiers. Rectifier is a circuit which converts an AC input voltage or current into DC voltage or current. So this process is called as rectification. You can consider that the rectifiers converts AC input voltage or current to the DC voltage or current. So we are going to divide the rectifiers into two types. So consider that half wave rectifier and the full wave rectifier. Again, in full wave rectifier, we are going to consider the two types. First one is center tap rectifier, second one is bridge rectifier. In that, so we are going to study the half wave rectifier, the half wave rectifier operation, then half wave rectifier efficiency derivation, then ripple factor derivation. Then we are going to study the full wave rectifier. In that full wave, considering the center tap rectifier and bridge rectifier. So why we are going for the center tap rectifier, then why we are going for the bridge rectifiers, that we are going to study in the coming slides. Consider the half wave rectifier. So in that name itself takes half wave, so that we are considering only half wave in the input side. Consider a circuit consists of the transformer, the diode and load resistor. Transformer, you can consider that in that step up transformer and step down transformer. Says the voltage is increased and voltage level is reduced. Here we are going to use the step down transformer. So we are going to convert the 230 volts AC input to the 12 volts or 5 volts AC then. Here we are going to consider the sine wave. Consider a 230 volts AC input that we are going to convert into 12 volts, that we are going to give it to the diode. The diode is a semiconductor device. It's having two terminals, anode and cathode. It conducts only in the forward bias condition. So once the input voltage is greater than the diode threshold voltage or diode cutoff voltage, diode start conducting. So it's considered as a closed path. Consider that the input, the positive cycle. So the voltage is increased to 0.7. The diode cutoff voltage is 0.7. Once that voltage, input voltage increases or crosses the 0.7 volts, diode starts conducting. So it becomes the closed path, so that the current will flow. So in that, so whichever the input is present in that the secondary transformer, that will appear across this resistor, so that we are going to get that whichever the input you are considering, that output is follows the input. So consider in the negative cycle. So during the negative cycle, so you know that the diode won't conduct in the reverse bias condition. So we are going to give negative supply to the anode. So diode won't conduct, so it becomes open circuit. So open circuit means the current will not flow, so that voltage across that the load resistor or output across the load resistor is 0. So that we are going to consider the straight line is 0. Similar way in the next cycle. So again the positive cycle will come. So again diode will conduct in the forward bias once. So diode conducts, it becomes a short circuit. Your output follows your input. Whichever the output is there, that will appear at the load resistor. Here you can observe this waveform. This is AC input waveform. So resultant output waveform, or you can call it as the output across the load resistor. This you can consider VDC equivalent circuit. The threshold voltage you can consider as the Vmax, maximum voltage, that you can call it as Vm. So we should know that during the positive off cycle, diode is forward bias and acts as a closed circuit, and during the negative off cycle, diode is reverse bias and it acts as a open circuit and no current flows. The current flows in a closed path only. That. Consider average or DC current. So consider this waveform. This is the input voltage, or you can call it as that sinusoidal waveform. In the positive off cycle, diode D1 will conduct, so that the same input is appeared at the output. In negative off cycle, diode won't conduct, so that output is 0. Similarly, the positive off cycle, it will conduct. So we need to consider that the maximum voltage, that we can consider as a Vm, and we need to consider a DC voltage, that the direct current voltage, where written as line. So we need to represent that average or DC the current. So we need to assume that the cut-in voltage of the diode is 0. So we can consider that. So diode will operate in the different the modes. We can consider the ideal model, we can consider, then approximate model, then piece-wise model. In the ideal model, when that voltage is increases, that so once the voltage is greater than 0, diode will start conducting. So in that we are going to consider ideal diode condition. The diode voltage is 0 and the forward resistance of the diode, we are going to consider that is also 0. That. So that we are going to get the same input appeared at the output side. We can consider that VL is equal to Vs during the positive off cycle of the Vs. So VL is equal to 0 during the negative off cycle of the Vs. That. So this is the positive off cycle, this is negative off cycle. Consider the peak current. That when we are going to consider peak current, so we know that the Ohm's law, so V is I into R. You can consider that I is equal to V by R. So Im can consider maximum current is equal to the maximum voltage divided by Rf plus RL. RL is the load resistor, Rf is that forward resistance. So when you are going to find out that the practical values, so we need to consider that the forward resistance, that we cannot consider the forward resistance or diode resistance is 0. When you are going to use practical, is having some resistance. Consider Im is equal to Vm divided by Rf plus RL. Then the average or DC value of the load current is, we can consider that IDC is equal to 1 by 2 pi, so integration of 0 to 2 pi IL into d omega t. So IL into d omega t, when you are going to represent the sine wave, so we can consider as Vs is equal to, we can write it as Vm sin omega t. Vm sin omega t. Similar way, so we can write it as Is is equal to, or IL is equal to Im sin omega t. So that we are going to substitute here. IDC is equal to 1 by 2 pi, 0 to pi, because we are considering only 0 to pi, that the input, because we are going to get the output is 0 to pi. So pi to 2 pi, this output is 0. Im sin omega t into d omega t. So diode conducts only 0 to pi. So the pi to 2 pi, diode won't conduct. That is negative cycle. So we can simplify this equation so that we can take the Im outside. Im by 2 pi. Sin omega t is, so minus cos omega t. So minus will take it outside. So cos omega t, we can substitute that limit 0 to pi. So when we are going to substitute that 0 to pi, so cos 180 is minus 1, cos 0 is minus of cos 0 is 1. So minus into minus, minus 1 plus minus 1 becomes minus 2 will get. So that minus minus will cancel. So IDC is Im by pi. So this 2 will get cancelled. IDC is equal to Im by pi. Should know that in the off-wave rectifier, the DC current or average DC current, I can consider as IDC is Im by pi. Consider DC voltage across the load is VDC is equal to IDC into RL. You know that the Ohm's law, V is equal to I into R. So considering the DC voltage, so we can write that VDC is equal to IDC into RL, because we are going to take that the DC voltage across the load resistor. We can substitute that IDC value. We already calculated that Im by pi into RL. So what is Im? So we know that Im is Vm divided by Rf plus RL. So that we can substitute that Vm divided by Rf plus RL instead of Im. So we can take that RL divided by Rf plus RL. We can take it separately, that we can write as 1 plus Rf by R. So we can write that VDC equation is Vm divided by pi into 1 plus Rf by R. Since the forward resistance of the diode is very small compared to the load resistor, so that we can write it as Rf is very less compared to the RL. So we can neglect that. We can take it as VDC is Vm by pi. So when you are going to solve the problems, this is theoretical, the formula that VDC is equal to Vm by pi. When you are going to solve the problem, if they are going to mention that the forward resistance of the diode, so we need to take this equation one step before that, the final equation, we need to take that, so that we are going to consider the forward resistance also. So we are going to get that exact the DC voltage. The next is RMS value of the load current. So we have to find out that the DC currents, VDC and IDC then. Now we need to find out the RMS value. So we need to consider that IRMS, root mean square value of I current, is square root of 1 by 2 pi integration from 0 to 2 pi IL square into d omega t. Here the same, that IL is equal to sin Im sin omega t. So consider that 1 by 2 pi. So we need to take that the wave is 0 to pi only, because diode will conduct in the positive half cycle only. So we can consider 0 to pi Im square sin square omega t into d omega t. So IL is Im sin omega t, square is there, Im square sin square omega t. So simplify this equation, you are going to get IRMS is Im by 2. When you are going to consider the simplification, 1 by 2 pi is there, so you can take Im square outside. So sin square omega t is there, sin square omega t we can write it as 1 minus cos 2 omega t divided by 2. So we can take it 2 outside. So 1 minus cos 2 omega t. So integration of 1 minus cos 2 omega t is, so integration of 1 is d omega t and integration of cos square 2 omega t. So when you are going to apply the limits from 0 to pi, that term becomes 0. Then you are going to apply the limits to the d omega t or t. So limits is from 0 to pi. So that we are going to consider the pi value. So that pi will cancel in that equation. Then 2 into 2 is 4 is coming. Then Im square. So that the equation before this equation is square root of Im square divided by 4. So that we can take it outside. The square root Im square is there. Square and square root will cancel. Square root of 4 is the 2. So that the RMS value is Im by 2. So next value is IRMS voltage. You know that. So Ohm's law says V is equal to I into R. So that RMS is equal to IRMS into RL. So you can take Im by 2 into RL. Then what is that Im? Im is Vm divided by Rf plus RL. So you can substitute that. So we can simplify that. We can write that Vm by 2 into 1 plus Rf by RL. Since Rf is very less compared to RL, so that we can neglect, we can write the equation VRMS is Vm by 2. But when you are going to do it in the practicals or in the practical value, so we need to consider that the feedback or forward resistance. Consider the power conversion efficiency, means the efficiency of half-wave rectifier. So we can write that efficiency symbol is just like this. So it is defined as ratio of DC power delivered to the load to the AC power supplied from the secondary of the transformer. So we can write it as the equation. So neta is PDC divided by PAC. So for that we need to find out the PDC value. So you know that the power equation is P is equal to V into I. We can write it in this different fashion, that P is equal to, so V into I, or you can write it as P is I square R. So when you are going to consider that P is equal to I square R, so in this form V and I square R, when you are going to consider the DC and AC, so that I square R, the current is having that IRMS current and IDC current. So that it will be easy when you consider that the P is equal to I square R formula. So PDC is IDC square into RL. So that what is that IDC? IDC is Im by pi. So that IDC square is Im square divided by pi square into RL. This is the PDC value. Then consider the PAC value is IRMS square into RF plus RL. When you are going to consider the power of AC, so we need to consider that the forward resistance of the diode also. So that we can consider IRMS square into RF plus RL. IRMS is Im by 2, so that IRMS square is Im square divided by 4 will get into RF plus RL. So substitute that. This is PAC value and this is the PDC value. Substitute that PAC and PDC value in this equation. So that Im square into RL divided by pi square is PDC divided by Im square RF plus RL by 4 is PAC value. So in that, so Im square will get cancelled. The 4 by pi square into RL divided by RL plus RF. So this, when I am going to consider this, the equation RL divided by RF plus RL. So consider that RF is very small compared to the RL. That RF we can consider is very small compared to RL. So we can neglect that. So this term we can consider in the theoretical value is 1. So that 4 by pi square. 4 by pi square is 0.406. So we can consider the efficiency is 40.6% efficiency. The efficiency of half-wave rectifier is 40.6%. This is the half-wave rectifier efficiency. Means 40% of the DC you are going to get from that the 100% AC. Next, consider the ripple factor. Ripple factor, it is defined as ratio of the RMS value of the AC component of the voltage or current to the DC value of voltage or current. So you can write it as IRMS divided by IDC. The formula you can write it as the square root of IRMS square minus IDC square divided by IDC, because IRMS square is equal to IDC square plus IR square into RMS square. The formula we are going to use is generally that the ripple factor is square root of IRMS divided by IDC whole square minus 1. Substitute that value. IRMS is Im by 2, IDC is Im by pi, so whole square, so that Im square and Im square will get the cancel that. Then you can consider pi square divided by 4 minus 1. Can simplify that pi square divided by 4 minus 1 and the square root of that value. So you are going to get ripple factor is 1.21. So 1.21, that indicates that in half-wave rectifier the AC component across the load is 1.21 times of the DC component. So 1.21 times of that of DC component. Okay, so 1.251 times of DC component, so we are considering here. Okay, so that we need to consider that AC component across the load is 1.21 times of DC component. Means so 1.21 times of DC component of AC is present at the load. Full wave rectifier. In that full wave rectifier, we are going to consider the two types, that is 2 diode center tap rectifier and the bridge rectifier. Consider the 2 diode center tap rectifier. Here we are going to use 2 diodes and center tap transformer for designing. So that's why you are going to call it as 2 diode or center tap rectifier. Consider the circuit. So in that we are having a transformer, 2 diodes and 1 load resistor. So consider the transformer we are going to use as a center tap transformer. In that, so we are having 2 inputs and 3 outputs in the transformer. So you can consider that center tap transformer. So exactly center point from the coil, secondary coil, we are going to take the point or the connection. Here, so it's going to give, so from 0 to A and 0 to B. 0 is the origin you are going to consider from the secondary coil. So this gives the positive side and this gives the another negative side, so that we can consider. So 230 volts we are going to convert into 12 volts, means from the center tap 0 to plus 12 volts you are going to get, and on the other side you are going to get minus 12 volts. So here we are going to use the 2 diodes. So one diode is for the positive cycle, another diode is for negative cycle. Now consider that the waveform. So we know that we are going to apply the sinusoidal input, or you can call it as AC input. Here we are going to consider so the transformer going to reduce the voltage level, or we are going to increase the voltage level. So two types. So is we can consider the step up transformer and step down transformer. Here we are going for the rectification purpose, so we are going to use step down transformer. Now, so we are going to consider that in the positive off cycle, diode D1 will conduct. So how means? So in the positive side, so D1, say here positive supply you are going to apply it to this anode of the D1, so that diode will be a forward bias. So once it's forward bias with respect to that the center tap point, so the connection will be closed, so that whichever the input is there, that will be appeared across the load, so that output is the follows the input, and one more, that input is appeared at the output point during the positive off cycle. During the negative off cycle, you can consider here during the negative off cycle, so diode D2 will conduct, diode D2 will becomes the forward bias, and that negative cycle is appeared at the output side, that is not at a negative cycle, so that positive cycle only we are going to get at the negative, for the negative cycle of the input. Then that will be continuous, so that both in the positive cycle and the negative cycle, so we are going to get the output. Positive cycle diode D1 will conduct, and in negative cycle diode D2 will conduct. For that you can observe that the voltage across the load and current across the load, VL and IL, the waveforms. So we can consider that the maximum voltage is Vm and maximum current is Im. We can consider the VDC, DC voltage, DC current. Finding out the average or DC currents, we can call it as IDC. Average or DC voltage, we can call it as VDC. Consider the sine wave, so we can consider the supply voltage, we can represent Vm sin omega t. Vm indicates the voltage, maximum voltage. Consider that the cut-in voltage of the diodes are 0. So you can consider we are using the ideal diodes, and Rf is the forward resistance of each diode. So we are going to consider the forward resistance. The peak current is Im is Vm divided by Rf plus RL. We can consider, so I is equal to V by R, so that we are considering the maximum current is the maximum voltage divided by the total resistance in the circuit. Total resistance is load resistor plus the forward resistance. Then we are going to find out the DC value of load current IL. We can find out that, so IL is, we can write it as IL sin or Im sin omega t. So you can consider the equation IDC is 1 by pi 0 to pi IL d omega t when you are going to find the DC current. So why means we are going to consider only the off cycle. Okay, so we can substitute that IL value is Im sin omega t, so we can integrate that sin omega t, so it becomes the cos omega t. So 2 Im by pi you are going to get. IDC is 2 Im by pi. Consider the DC voltage across the load. You can call it as VDC. VDC is IDC into RL. So V is equal to I into R. This is according to Ohm's law. So V voltage we need to consider as a DC is, the current is also considered as DC. IDC into RL. So IDC value are calculated 2 Im by pi, so that you can substitute the 2 Im by pi in this equation. 2 Im by pi into RL. Now, so we are going to represent with respect to Vm, so that Im is Vm divided by Rf plus RL. So you can substitute that Im value. Im is Vm divided by Rf plus RL. So from this we can take it out that, so 2Vm divided by pi, so into means divided by 1 plus Rf by RL. So this Rf is, the forward resistance is very less than the RL, so that we can neglect. So this value becomes 1, so that we can write it VDC is 2Vm by pi. You can consider this. So the DC voltage across the load is 2Vm by pi. Now consider the RMS value of load current and RMS value of load voltage. So for that, to consider the RMS value of load current is IL. So for that, IRMS value, we need to find out the root mean square value. For that, IRMS is equal to square root of 1 by pi. So integration from 0 to pi, IL square d omega t. We know that IL is Im sin omega t. When you go to substitute value, that will be square that. So you can substitute that value, Im square sin square omega t into d omega t. So simplify this equation. So Im square sin square omega t into d omega t. So Im square you can take it out. So that Im square by pi, sin square omega t is there. Sin square omega t we can write it as 1 minus cos 2 omega t divided by 2. So that we can substitute that. Then so we can take that 2 denominator 2 outside. So when I go to substitute the limits to 0 to pi, when I am going to integrate the cos 2 omega t, so the term becomes 0, so we are not considering that. The RMS value of load current IL, so when I am going to substitute the IL value, Im square sin square omega t into d omega t. So sin square omega t we can write as 1 minus cos square omega t divided by 2. That 2 we are going to take it outside this. So when I am going to integrate 1 minus cos square omega t into d omega t, this term, so this becomes 0 when I am going to substitute that 0 to pi limits. So only we need to apply the limits to 0 to pi 2. So integration of 1 is that t or omega t. So when you go to apply the limits, so we are going to get the pi value. The pi will get cancelled. So we are going to get square root of Im square divided by 2. So we can take the square root out. IRMS square is Im by root 2. This is the RMS, the current and voltage that we can consider. IRMS we are find out that. So we need to find out the RMS voltage. RMS voltage we are consider as VRMS. So VRMS is IRMS into RL. So you know that the Ohm's law, V is equal to I into R. VRMS is IRMS into load resistor. We know that IRMS is Im by root 2 into RL. We need to represent this equation in terms of Vm, so that Im value we are going to substitute. So 1 by root 2. Im is Vm by Rf plus RL into RL. So that we can take, then we can write it as Vm by root 2. So RL divided by Rf plus RL is 1 divided by 1 plus Rf by RL. Here denominator 1 plus Rf by RL. So Rf is very less than RL. So that you can neglect this term, that is this term becomes 1. So final equation of VRMS is Vm by root 2. So this is the equation. RMS current is Im by root 2 and RMS voltage is Vm by root 2. So we need to consider these two. So RMS voltage and current when you are going to solve the problems. Consider the power efficiency, power conversion efficiency, or you can call it as efficiency of full wave rectifier. Now, what is efficiency? Efficiency is defined as the ratio of DC power delivered to the load to the AC power supplied from the secondary of the transformer that we are considering. So DC power delivered to the load is equal to the PDC is IDC square into RL. So we know that P is equal to I into R. P is equal to, you can write as I square R. So you can write as P is equal to V into I. So we are going to use P is equal to I square R. So we are considering the DC power, so that we can use DC current IDC square into RL. Now we need to substitute that IDC value. So we have discussed that. So when you are going to find out that DC current and DC voltage, the DC current is IDC is 2 Im by pi. So that you can substitute that IDC value 2 Im by pi, so whole square into RL. So this is the PDC value. So consider the AC power supply from the secondary of the transformer. AC power supply is, so PAC is IRMS square into RF plus RL. When you are considering that the AC alternating current power, we need to use RMS value. IRMS square into RF plus RL. What is IRMS square? The current. So IRMS square is, the IRMS value is Im by root 2, so that you can substitute that Im by root 2 value. Im by root 2 whole square will come into RF plus RL. Now, so we need to substitute to the efficiency equation. We know that efficiency is PDC divided by PAC. This is ratio of, so DC power delivered at the load to the AC power supplied from the secondary of the transformer. That is, DC power is PDC and AC power is PAC. So we already calculated individually, so that you need to substitute in that equation there. PDC is 2 Im square divided by pi into RL. Then PAC is Im divided by root 2 whole square into RF plus RL. Now, so from this equation, so we can write it as the 4 Im square into RL divided by pi square in the numerator. In the denominator, Im square divided by, this is the square root square, means that it becomes 2. So this Im square will get cancelled. This 2 we are going to consider, that 2 will goes to the, so numerator part, that becomes 4 into 2 is 8. 8 divided by pi square into RL divided by RF plus RL. So that RL divided by RF plus RL, we can write it so as 1 plus denominator is, so when you are going to divide that 8 divided by pi square, you are going to get 0.81. So 0.81 divided by, so 1 plus RF divided by RL, otherwise 0.81 into RL divided by RF plus RL also we can write it. So we can consider this 1 plus RF by RL. So when you are considering RF value is less than RL, so that, so this term becomes, denominator term becomes 1. So we can write as the efficiency is 0.81. Efficiency is 0.81. So or you can write it as is 81%. So we know that for half wave rectifier, the efficiency is 40.6%, that will be doubled in a full wave rectifier. So we are considering both the cycles, that we are going to consider off cycle, positive off cycle, and also negative off cycle. So that efficiency is 81%. The maximum value of efficiency of the full wave rectifier is 81%, corresponds to the value of RF by RL is equal to 0. When you are going to consider RF by RL, you are going to negligible, then we can consider as this is the 81% is theoretical value. When you are going to consider the forward resistance of the diode also while considering the practical, so in that time, so it's almost near to that 81%, not exactly 81%, it's almost near to that, the 1 or 2% less or more we are going to get that. So we are going to consider some resistance means, so moreover that we are going to get 1 or 2% less from this 81%. Consider the ripple factor. Ripple factor is defined as the ratio of RMS value of the AC component of the voltage or current to the DC value of voltage or current. Means it indicates that 0.48 times of DC components of AC is present at the output side. So that we can write as ripple factor is IR RMS divided by IDC. So IR RMS we can write as I RMS square is equal to IDC square plus IR square into RMS. So we can take that IRMS minus IDC square. So square root of IRMS square minus IDC square divided by IDC. When I go to simplify this, the square root of IRMS divided by IDC whole square minus 1. Substitute the IRMS value. So we know that IRMS is IM by root 2. Substitute that IM by root 2. IM by root 2 whole square divided by IDC value is 2 IM by pi. Substitute that 2 IM by pi whole square minus 1. I am going to simplify this, IM square divided by 2. So inside that square root, IM square divided by 2 divided by 2 IM square means 4 IM square. 2 IM whole square is 4 IM square divided by pi square. So that IM square will get cancelled. Okay, so pi square divided by 8. You can consider, so 1 by 2 divided by, so 4 divided by the pi square minus 1. So that you can take it that the pi square divided by 8 minus 1, so square root of that value, so pi square minus divided by 8 minus 1, so that is substitute that, so pi square is 3.142, so 3.142 square, so divided by 8, that value is 1.23 minus 1, so 0.23, the square root of that answer, so you are going to get 0.48. So ripple factor is 0.483. So it indicates that in a transformer, this full wave rectifier, the DC component across the load, DC component means AC component across the load is 0.483 times of DC component. Means 0.83 times of DC component, that much amount of AC component is present at the load, that we need to consider that. Thank you.